Okay, so I don't want to call it exciting information, but information nonetheless. So I gave you a handout. On one side, it has guidelines to try a 3D molecule. Please bring that sheet with you from now until December. I know you're like, that's forever. It is. But everything we learned today, we will use to move into 3D. Those of you who are just rolling in, I will get you a handout. You can get it in a second. So please keep that. The other side is the bond enthalpy tables, which are kind of like the delta H, not F tables. It'll help us on Wednesday's lecture. Alex. So there are 2 remaining OpenPi sessions this semester. OpenPi means you could do anything you want. All those objectives where it says, ooh, I want you to practice some more, you could look at anything you want. There are no restrictions. So those times are Thanksgiving, starting at 12:01 a.m. on the 23rd, and it ends on the 27th, which is Saturday night, I think. During that time, you can access anything you want. You can also do that December 11th through the start of the final exam. So there is a knowledge check between Thanksgiving and Christmas, or Thanksgiving and finals. So there is time in there. You'll have to look at that. So the way this works is we have objectives due today from last week. Next Monday will be the stuff from this week. There will be objectives due on Monday, the 29th, which is the Monday after Thanksgiving, from the Monday of Thanksgiving. Then we go back to normal life. 2 things. During OpenPi, it will basically open up and you can click into any module, so you can be like, I'm going to do what's coming up, or it will unlock everything from the past. If you have questions, I'm happy to assist. As we move forward, it just gives you a little bit more time to basically say, I hate this objective, I'm going to learn it again. Questions, comments, concerns?
Is it November 27th at 11:59 a.m.?
I think so. I'm going to double check. Because I'm pretty sure they're all set up to expire at midnight. So basically the 23rd is as soon as the objectives to next Monday's end. You'll have, I don't want to call it a free-for-all because that sounds terrible, but you have a free-for-all from Monday or Tuesday morning at 11 or at 12:01 through 11:59, I think, on Saturday. So that when you're done with your family, you can do something else. Any other questions about Alex? Yeah. It needs to be in your learned bucket at the start of the final. So you can, you know the objective, the limiting reactants in solution 1 that everyone's like, this is terrible. If it goes in and out every time, just leave it alone until the OpenPi at the end of the semester. Because every time you have a knowledge check, Alex is going to be rude and be like, excuse me, no. You just need to have it in a blue category. Because I think there's a status bar at the top, and it goes from like learned is light blue and mastered is dark blue, give or take. It just needs to be blue. Any blue works for me. So when you sign in, the pie at the center where it gives you like a, 12%, 90%, whatever that is your pie score on the last day. Other questions? Because I will forget. If you have arrived momentarily and do not have a copy of this handout, I know there are people in it. Where are you hiding? Anybody else? So when we last hung out, which was last Wednesday, we ended our class talking about dipole moments. So dipole moments and bond polarity tell us a couple of different things. So this is the electronegativity trend, which basically states the following. It increases as you go across and decreases as you go down. And the idea is that we can use that to determine the polarity of a bond. So from 0 to 0.5, we're chi1 minus chi2, or the absolute value of chi1 minus chi2, chi being the electronegativity. These are nonpolar. From 0.5 up to 2.9, these are polar covalent. And 3.0 to 4.0, these are ionic. Regardless of the value, if you have a metal-nonmetal, it is ionic. So when we think about this, what we are thinking about is the distribution of electrons around two atoms. So we looked very briefly at these dipole moment drawings last week, where we can say for F2, or the fluorine-fluorine compound, it's green. Green means that it's equally distributed. No one side of that element is more negative than the other. Whereas if we look at HF, we have a distinctly red side. That means that the negative electron spends more time on the fluorine than it does on the hydrogen. So when we look at HF, what we see is a delta plus and a delta minus. Delta meaning partial. And so we can annotate that as such, or we could draw that with a dipole arrow. Now, the arrow has a couple of things. This side has a positive sign. The positive sign goes on the electropositive element. Electropositive meaning the one that has a smaller electronegativity. The arrow head points in the direction of the negative charge. So this is a dipole moment arrow. So if you're asked to draw the dipole, what we're asking for you to is draw this structure. It is important that you have both the arrowhead and the tail has a positive sign on it. Just having an arrow without the positive tail doesn't mean the same thing in this case. When you think about this, if we have hydrogen, fluorine, this has the positive sign and this has the negative sign. So you basically just connected those two structures and made an arrow out of one side. Electropositive basically means that it's not electronegative. That's all that means. It's just a fancy way of saying it has a low electronegativity. Or it is less electronegative than the other side. Questions thus far? So, I don't want to say a non-shocking twist, but it's strength of one. So we're going to think about it. Now we're going to calculate it. So it turns out that when we think about this region of polar, it goes from 0.5, which is basically nonpolar, all the way up to as polar as you can be without being ionic. That means there's this range. And so when we think about that, you could draw it structurally like this HF, where it basically gets more or less disparate. We can also calculate the strength of a dipole moment. So we can use an equation where mu equals Q times R, where mu is the dipole moment. This is measured, the units for that is divide. And divides. And the charge, this is the charge. This is in coulombs. And this is the bond length. needs to be in meters. So there is going to be a conversion because meters times coulombs does not equal Debye. So 1 Debye is equal to 3.34 times 10 to the negative 30th coulomb meters. This is a unit conversion. This is in the same place as you find other unit conversions, like 101 joules in 1 liter atmosphere. It's already on your equation sheet. It's been there. You just haven't had to use it yet. So let's look at some example calculations for this calculation. It turns out that the dipole moment is a relatively, it feels complicated because there are many unit conversions, but the reality is this is very similar to our calculation that we looked at in chapter 1. So we're going to calculate the dipole for a 1 angstrom bond with full charge separation. Meaning, if we have two elements, x and y, x is negative and y is positive. So in this case, we don't really have a bond. It's more like an ionic compound with a 1 angstrom bond. From here, we can set up this calculation. We are looking for mu, and that equals Q times R. Now, Q is the charge. Charge, in this case, is -1. Now, -1 is not in coulombs, so we need the charge on the electron. Where in this case, it's 1.60 times 10 to the negative 19 coulombs. This is in the same place as this on your equation sheet. It's just a number we haven't looked at yet. Multiplied by 1 angstrom, and we're looking for this in Debye. So you can multiply these together, and your value is in coulomb angstroms, not Debye's. So we need to convert. So 1 angstrom is 1 times 10 to the negative 10 meters, also on your equation sheet. Now, 1 Debye is 3.34 times 10 to the negative 30th coulomb meters. So from here, our value is going to be in Debye as we had hoped. So we're going to get 4.79 Debye is the dipole moment on a fully charged separated value, 1 angstrom apart. Questions? Yeah.
Where's that constant represented again? The 1.60 times 10 to the negative 19.
This. Thank you. It's okay. I was like, which one? This is the charge on an electron.
Oh,
So it is a value that we talked about like way back in chapter 2. Please don't memorize it. It is on the equation sheet. All you gotta do is remember that that's what you're looking for. Other questions? So let's look at a different type of calculation. Well, the same calculation we're going to solve for something else. For the HCl bond that is 1.27 angstroms, if the dipole is 1.08 Debye, what fraction what fractional charge in terms of E are there, are on Cl. So in this case, we're going to take the calculation on the left, and we're going to kind of look at it in a different way. So we know that the HCl bond has a dipole moment in this direction. We know that based on the electronegativities. what we're calculating is what is the delta plus and what is the delta minus. Is it what part of the electron is on this side? So in this case, we're going to use the same equation, just different. That sounds kind of cheesy. So in this case, we are going to solve for Q, which is equal to mu divided by R. From here, it's just basically equation unit manipulation. So in this case, mu is 1.08 divided by 1.27 angstrom. 1 angstrom is 1 times 10 to the negative 10 meter, and 1 divide is 3.34 times 10 to the negative 30th coulometers. So we can plug this into our calculator, and hopefully you will also get 2.84 times 10 to the negative 20th coulombs. Now, this asks for a value in terms of electron. In order to convert coulombs into electrons, we're going to use this value because 1.60 times 10 to the negative 19 coulombs is the charge on one electron. So we can basically take the charge on one electron and determine that it's 0.178 electrons. So delta minus here is a negative 0.178, and the delta plus over here is plus 0.178. Because the charges have to be equivalent, what we're seeing is that the electron spends roughly 18% more time here than it does here. So we are asking and we are quantifying how strong or weak that dipole moment is. What questions do we have in this moment? Yeah. This is if you plug this into your calculator. This equals that. The next one is the charge on an electron.
And that's standard for all electrons?
What you're thinking is like, so if there were to be like a -2 charge, it would be 2 times that value. But in a dipole moment, you don't have, it's going to be fraction of an electron. You can't lose, 2 don't go. That's just like the simplest way to put it. Other questions?
The 1.0 times 10 to the negative 19, that was assuming that they have a charge of, was it 1 or negative 1?
-1, but that's a 1.6. It is, the charge on an electron is 1.60 times 10 to the negative 19 coulombs. Good question. So why do we care about dipole moments? Dipole moments allow us to, one, we can use that in the ability to create a molecule or a structure. What we are going to do in chapter 9 is we're going to create 3D molecules and ask, is this whole thing polar or not? Now you might be like, we haven't even learned how to draw in 2D. That's where we're going, like right this second. But we want to be able to think about the polarity. This is what gives rise to the structure of ice, why it is less dense. When we think about collated or colloid solids, basically anything that cool happens in water is due to the polarity of water, and so we can start to quantify that. Any questions about dipole moments? So for the next, 20 minutes, 15. I wish I could see the clock. But for the next little while, we're going to start to think about Lewis dot structures. So, what I would like you to do while I erase the board and verify that everyone has a copy of this handout, I want you to read the guideline. for both formal charge and the Lewis dot structure. So basically the first two structures, so there's part 1, part 2, part 3. Read the first two. Anyone not get a copy of this handout? So I would keep a hold on to this handout while we think about drawing Lewis. And between now and the end of the semester, conservatively, you will draw 50. Realistically, you will draw probably 100 different Lewis dot structures. Many in class, many in homework, many as you study. Use the guidelines. They should not steer you astray. Well, they definitely won't if you follow them as intended. So the guidelines are pretty simple. 1, sum up all the valence electrons for any given atom. 2, write the symbols for the atoms connecting adjacent atoms with a single bond. Most of the time, I will underline the central atom. If it is something followed by something else and multiple of that, more often than not, the first thing is the central atom. If there are 3 different elements in a row, you connect them in that order. If on a graded assignment, I forgot the underlines, you can always ask. It's not meant to be a secret. It's not meant to be hard. I try to always do it, but sometimes the formatting gets stripped out of my files and it just happens. So once there, we want to complete the octet around all atoms connected to the central atom. Any remaining electrons go to the central atom. If there are not enough electrons left for octet on the central atom, multiple bonds are required. So with this information, let's look at some practical examples. So for PCl5, PCl3, the first thing we're going to do is the number of valence electrons. Phosphorus has 5 based on its location in the periodic table. There are 3 chlorines at 7 apiece. So 21 plus 5 gives you 26. Now we know the number of valence electrons. From here, step 2 tells us, okay, we want to put the central atom and connect everything else. Phosphorus connected to 3 chlorines at 90-degree angles. So we've used 6 of our valence electrons. From here, we want to just start completing octet on everything on the outside. My recommendation is to go 1 element at a time. They need 8 electrons. Each lone pair should have 2, and a bond counts for 2. So now we have used 24 of our 26 electrons. The last 2 get dumped on the central atom. So now we've used all 26 of our valence electrons. So we double check. Does everyone have octet? 2, 4, 6, 8. All the chlorines look the same. We can make an assumption they're all the same. Phosphorus, 2, 4, 6, 8. Sounds good. This is the basic structure for how you complete or achieve a Lewis dot structure. Questions? So last week, I told you to draw the Lewis dot structures for any element and then start sticking them together. That works sometimes. I would recommend that you move to this method where we count the valence electrons, create octet, move around. So when we look at the next one for HCN, carbon is our central atom for 2 reasons. 1, it's underlined, but 2, it's in the middle of this structure. So when it's 2 or 3 atoms, if you have carbon monoxide, CO, neither of them are really central atoms. Again, if you're ever confused, I will happily answer that on an exam. So we have HCN, our valence electrons in this case, 1 plus 4 plus 5, that gives me 10. Hydrogen connects to carbon, connects to nitrogen. So octet for hydrogen is 2, satisfied. Nitrogen needs another 6 electrons. We've now used all 10 of our valence electrons. Does carbon have octet? No. I don't want to say what is octet, but octet requires 8 valence electrons, right? So we've got to figure out how to create a sharing environment. In this case, nitrogen has all these lone pairs, and so what it's going to do is it's going to create additional bonds between carbon and nitrogen. If we add 2 additional bonds, now all of our elements contain octet. We can see that nitrogen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8 as well. Hydrogen only needs 2 and it has 2. In ALEX, it asks you often to count up the bonding pairs and the lone pairs. For nitrogen, it has 1 lone pair and 3 bonding pairs. You just count them up. It should only ask about it in terms of a single element, right? So it's not going to give you like 100 different choices. It's going to give you something consistent. What questions do we have thus far?
Does it matter where the valence electrons on nitrogen? Does it matter if it's on top, bottom, right?
No. When we move into VSEPR, yes. So sometimes I do things because I know where it goes in 3D. But in terms of Lewis-Dot structures, there are no restraints. You just need to be at 90 degrees from one another. Other questions? So one of the things we want to start to think about is what happens if we start to have charged molecules. So we're going to look at BrO3 minus. So we have 7 plus 6 times 3. And we're going to add an extra 1. And we're going to do that because it has a negative charge. If you have a positively charged molecule, it has 1 less electron. It doesn't matter who gains or loses the electron. The molecule overall has a +1 or a -1. This gives us 26. So now we can start to follow the same rules. Bromine in the middle. Add all of our oxygens. We're going to start just adding lone pairs. So now this is the structure that you should get once you make a valence or a Lewis-Dot structure. But we know that it has a negative charge. The thing is, we want to know who is charged. Because it will matter in terms of molecular structure. You can start to get weird elements that maybe shouldn't have a charge. But in this case, the question becomes, where is the charge? So if you read the book, I don't know, like all 5 of you, it makes a statement of like, we could put it in brackets with like a negative charge. We are skipping that step. We are going past the bracket land into where does the charge live. And we're going to do that using formal charges. So the formal charge is the ability for us to assign the electrons. And we can calculate that. If you look at this graphic, it's not a graphic, this is a list. We're in the second part. So formal charge. I will show you the way I do it. I'll also show you the way Alex is going to do it in their explanation. Both are correct. You just can't mix them. You can just pick one method that works in your brain and live with that. I'll show you why they are different and how they are mostly the same. So formal charge, Fc, is equal to the valence electrons, and this is per element. So for many of these, you'll run the same calculations like nitrogen, carbon, oxygen, and bromine. It's the valence electrons. So this we'll call the Malka Method, just to distinguish from the Alex method when I write on the board. It's minus half of the bonding electrons minus lone pair electrons. So once we have this, I'm going to switch to a blue marker because I feel like no one can see this because I can't see what I'm writing and I'm 1 foot away. I try not to write in colored markers. So this is my method. Alex tells you this is the formal charge. It's still the valence electrons, but it's minus the number of bonds. And then minus the lone pair electrons. So let's look at this for nitrogen in our HCN. So for nitrogen, so in my method it is 5 valence electrons because that's how many nitrogen has, minus half of the bonding electrons, 2, 4, 6, minus the lone pair electrons, and that gives you a formal charge of 0. Which is good, this molecule has no overall charge. The Alex method gives you 5, then you count how many bonds there are, 1, 2, 3, minus the lone pair electrons. It also gives you 0. The biggest difference is in how you handle the bonding electrons. The only reason I like to do half of the bonding electrons is because I think the lone pair calculation gets complicated. If you count up the number of bonds, for me, I would promptly then go on to count the number of lone pairs. And I would get the wrong formal charge. I know that it feels like you'll never remember this. This will become second nature, and it will be very easy as we move forward. Questions about calculations of formal charge in general?
Could you just run through that again?
Yeah. So it's the number of valence electrons minus half of the bonding electrons. So each bond has 2 electrons, 2, 4, 6, minus however many lone pairs are on that element. So the formal charge calculation is per element, not an overall charge. So let's look at BrO3 minus. We know it has a negative charge. The question is where? So I'm going to choose oxygen, mostly because it's on the outside. So the formal charge of oxygen is 6, which is the number of valence electrons, minus half of 2, minus 6, and that gets you negative 1. So now we have a negative charge on the oxygen. The way we draw that is to put a negative sign in a circle. We use a circle so that I can find it when I grade your paper. That's why. Now, is there anything different about this oxygen than this oxygen? No. So it turns out the formal charge is the same for every element that has the same electronic structure in this kind of graphic. So now in this molecule I have 3 negative charges and we know it's only a minus 1 overall. So you can do 2 things. 1, go, I think we did something wrong. Or 2, wonder what the formal charge is on that bromine. So let's look at the formal charge on bromine. It's 7 minus 2, 4, 6, half of 6 minus 2, and that gives you positive 2. So in this case, the bromine structure has an overall negative 1 charge, but each oxygen has a negative charge on it, and bromine has a plus 2 charge on it. What questions do we have currently meandering around our brains.
Are you going to access which one to find, or we have to find all of them? Or you need to like choose one?
For what I think you're asking, if this question were to be on the exam, you would need to know the formal charge because it has a negative charge. You need to know who owns the negative charge. You only need to write out the calculation for the oxygen once. I don't need you to write the same things 4 different times. Now, if your oxygens have 2 different structures, which we will not see today, but we will definitely see on Wednesday, then you might need to write it out more than once. But what we will see as we move forward is that its similar elements have similar charges. So what you'll begin to see is like, when oxygen looks like this, it always has a formal charge of -1. Where the other structures of oxygen may not. Any other questions?
Does it matter where the negative charge and the positive is? Put it on there, or it's just like what you like?
You need them to be next to the element that owns them. And preferably close enough that if they live there, I'll know that they live there. Fantastic. All right. We can stop here. We will take a mini exam. As always, if you do not have a calculator, I have a whole bin of them. Please get out your ID.